Hey guys, welcome back to the Biomechanics 1 lecture series. We're still looking at two-dimensional motion. I'm going to start you guys off with a concept test, well, in essence, two concept tests for this particular video. In the previous one, we looked at calculations for projectile motion. We discovered a couple of things in terms of how much time it takes a projectile to reach a certain height. The velocity at the top is equal to 0. Total time of flight is equal to the time it takes to go up and the time it takes to go back down. But all of those dealt with projectiles that were released and landed at the same height. So an object was released at a specific height, which is typically ground level. It goes through its projectile motion and it lands on that same level height. But in most situations, that doesn't tend to happen. In many instances, you have some kind of release height and landing height that is different. So how do our calculations change when we have to take those variables into consideration? So in this case, we've got a gun and a bullet. The gun is released with a initial horizontal velocity of 100 meters per second. So problems like this tend to trip students up quite a lot, and we'll try and break it down into its many component parts to see if we can make sense of it. The question tends to ask, what is the range of this bullet before it hits the ground, and what is its time of flight, or in other words, how long will it be in the air, right, before it hits the ground? So let's just try and unpack the values that we do have. So in this instance, the angle of release is 0, right? It's not being projected up, it's not being projected down, it is level, straight ahead. Okay, so your angle is just 0 degrees. You have the initial velocity in the x direction, which is 100 meters per second. Let me just undo that there. 100 meters per second. What is the initial velocity in the y direction? Well, the instant that this bullet leaves the barrel, its velocity in the y direction is 0 meters per second, right? Once it's in the air and it leaves this gun, then it's only subjected to gravity. Gravity is going to keep pulling it down all the time, and it's going to have some small initial velocity in the y direction, and then that's going to start getting bigger and bigger and bigger and bigger, so that by the time it's reaching the ground, it's going to have quite a big downwards velocity because acceleration is pulling it down the whole time, right? But the instant it leaves the gun, it has no component of its velocity acting in the y direction. In terms of its acceleration in the x direction, well, in this instance we're still ignoring air resistance, so it's 0 meters per second squared. Its acceleration in the y direction is just gravity, and because it's downwards, we're giving it a negative sign, which is equal to then negative 9.81 meters per second squared, right? What other information do we have? I think that's pretty much it. So let's see what we can do and how we can solve this problem. So most of our components deal with the y direction that we have. So again, we'll use our fundamental equations. So let's start off with this change in position. So the final position is equal to the initial position plus the initial velocity times time plus this 1/2 acceleration times time squared. Okay, remember we're going to break this into its x and y components as we've discussed in previous videos. So since we need to solve for time first, because before we can solve for range, we'll use the y equivalent of this equation. So it says that the final y position is equal to the initial y position plus the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times time squared. Well, we can simplify this a little bit. We already know that the velocity in the y direction initially is 0, so this 0 times anything will just be 0. So we're left with this specific version of the equation. We can also substitute this AY as being negative G, so I'll just put that in. I'm going to rewrite this a little bit. And I can take this initial Y over to the other side. So I'll have this final Y minus initial Y position is just equal to negative 1/2 GT squared. And remember that a positive times a negative, A is a negative G, will give us this. So then I'm going to multiply both sides by 2. So I'm going to have, and I can simplify this further, our initial Y position, we're taking our axis as being here, right? Level of the gun. The bullet's going to move down, it's going to end up in some position that's lower than what we started, right? So the initial Y position is also 0. And it's going to move down, so the final position is going to be some negative number. So in any case, I have Y, 2Y is equal to negative GT squared. I divide both sides by negative G, so I'll get 2Y over negative G. But remember, my final Y position is lower than what I had, so I'm going to put a negative there too to indicate that it was lower than where we started. The negatives tend to cancel, is equal to this T squared. So T is going to be equal to the square root of 2Y time divided by G. Now I can just plug in the values that I have. Yes. We are given this change in height. Remember, that's 2 meters above the ground where I start off with, so that's my Y position. So it'll be 2 times this 2. Gravity is 9.81. I'm going to square root all of that, which gives me a time variable of 0.64 seconds. So in essence, it says that from the time, the instant that the bullet leaves the gun, it's going to take it about 0.64 seconds to reach the ground. It's going to go down pretty quickly if it's only 2 meters above the ground. So you also realize that the higher this value is, the higher this change in displacement, or the higher the gun is above the ground, the bigger this value will be, and the longer the time will take. In any case, let's try and solve for the range. So that's another fundamental equation that we can use. Now we're trying to solve for how long it's going, or how far it will travel in the x direction. So remember, my final x position is equal to my initial x position plus my velocity in the x position times time plus this 1/2 a acceleration in the x direction times time squared. We know that acceleration in the x direction is 0, so all of this tends to simplify to 0, and I'm just left with this equation. I know that velocity in the x direction is, I'm already given that. So, and since my initial x position is relative to where I start from, this also simplifies to 0. I'm just left with this simplified equation, v0x times time. Well, I have both of those now. The velocity in the x direction was 100 meters per second times this 0.64 seconds, and it gives me 64 meters. Right, so this bullet will have traveled 64 meters before it reaches the ground. Okay, and those are your final answers. You've solved for time and you've solved for the range. Similar example, slightly different this time though. Let's say I start again with a gun, and I'll set up my coordinate axis like this. Right? Same principle, whereby the bullet is released with the same velocity of 100 meters per second, right? This v0. I have a target that's set up 200 meters away from where I set up my gun, and I want to find out, I need to adjust maybe my sightings or something. I want to find out how much is this bullet going to drop over this 200 meter time period. So I want to find out what is its total flight time going to be before it would reach this target, and by how much would the bullet drop over those 200 meters. Okay, so similar approach once again. I would need to try and solve for time, but this time we're working in a slightly reversed direction because I'm given more x variables, right, compared to y variables. So maybe a good place to start is to try and solve for x. So my final x position is equal to my initial x position plus my velocity in x direction times time plus my 1/2 acceleration in x direction times time squared, right? So we know already that this is 0 if we ignore air resistance. My initial position is 0 because that's where I'm starting from, so I'm left with this. My final x position is equal to my velocity in x direction times time. Well, I already have how far it's going to travel, and I'm interested in how long it's going to take to travel that distance. So if I rearrange this to solve for t, it would just look like this. That it is my x position divided by my velocity in the x direction. Right, that's 200 meters divided by 100 meters per second, which gives me 2 seconds, right? So it's going to take 2 seconds for the bullet to leave the gun and reach the target. The next goal is to see by how much did it drop. So since I'm then interested in a vertical variable, I'd have to look at the vertical components. So I'm saying that my final y position is equal to my initial y position plus my velocity in the y direction times time plus 1/2 my acceleration in the y direction times time squared. Okay, so I can simplify this a little bit. I know already that my initial velocity in the y direction is 0 for reasons that we spoke about just now. My initial position in the y direction is also 0 since I'm setting up my coordinate system from the gun. So I'm left with this simplified version or equation saying that my final y position is just going to be 1/2. Acceleration in the y direction is negative 9.81, and the time is what I've just calculated, 2 squared. And that would give me a value of negative 19.62 meters. Right? So in essence what it's saying that from the time that this bullet leaves the gun, it's going to drop by 19.62 meters, right? So I would have to adjust my sightings to account for this drop, right? Or I could fire this at some angle that would offset how much this would tend to drop, right? Because if I'm just going to shoot at this level angle, that's how much it's going to drop by. And yeah, if my height is not adequately adjusted, it would probably hit the ground before it hits the target. Okay, so those are things that you need to take into consideration. Remember that with these types of problems, where you have a horizontal setup without some kind of angle, right? Without an angle given, in essence what you're doing is you're just assessing 1/2 of projectile motion. So projectile motion kind of looks like this, right? In essence, you are starting to look at this problem from here. I'm setting up my coordinate axis and the bullet's going to travel and move down, right? So if it's traveling all this distance and it's going to start being pulled down by gravity, that's just 1/2 of the projectile motion. So you could start tackling it from that point of view as well. Yeah, I think that's pretty much it. I'll leave it there for now. We're going to look at a few more examples in the next video to really make sure that you guys are comfortable with all of the things that are happening.